Hello, welcome back. I was actually going to my bed, but let's read one more Pentium Pro. I have a Danish video I need to public. Just download a fresh copy. Yes, I have to add this Danish video. Yes, I have a playlist. Good. Let's continue. Soon it's 60, so I'm running out of time. So I have to continue all my small projects with my PDF and my Lego and my computer, my personal computer history museum project, my Lego, my comics, my pocket comics project, my Donald Duck. Because I'm running out of time, because I'm soon age 60. And I don't know how my life is in a few years, if I'm able to do YouTube, or if I like to do this, so we have to just continue. Yes, I need half a minute. To do myself ready in my bed, and I have to check my cell phone. Yes, let's continue.
Pentium Pro. Pentium Pro Intel Pentium Pro logo.svg. General information launched November 1, 1995, discontinued June 1998. Common manufacturer, S. Intel. Performance max. CPU clock rate 150 MHz to 200 MHz, FSB speed 60 MHz to 66 ms. Architecture and classification technology node 0.35 m to 0.50 microarchitecture 6 instruction set x86 physical specifications cores 1. Socket, S, socket 8. History predecessor Pentium successor Pentium 2 Pentium I Xeon. The Pentium Pro is a 6th generation x86 microprocessor developed and manufactured by Intel and introduced on November 1, 1995. 1. It introduced the 6P microarchitecture, sometimes termed i686, and was originally intended to replace the original Pentium in a full range of applications. While the Pentium and Pentium MMX had 3.1 and 4.5 million transistors, respectively, the Pentium Pro contained 5.5 million transistors. 2. Later, it was reduced to a more narrow role as a server and high-end desktop processor and was used in supercomputers like ASI-RED, the first computer to reach the trillion floating point operations per second, TRA-FLOPS. Performance Mark. 3. The Pentium Pro was capable of both dual and quad processor configurations. It only came in one form factor, to relatively large rectangular socket 8. The Pentium Pro was succeeded by the Pentium 2 Xeon in 1998. Contents: Microarchitecture Summary, Instruction Set, Performance, Caching, Available Models, Fabrication, Packaging, Upgrade Paths, Core Specifications. Pentium Pro, Pentium 2 Overdrive, Bus and Multiprocessor Capabilities, Pentium Pro /6th generation competitors. See also References, External links, Microarchitecture. The lead architect of Pentium Pro was Fred Pollock, who was specialized in superscalarity and had also worked as the lead engineer of the Intel IAP X432.4. Block diagram of the Pentium Pro S microarchitecture: 200 MHz Pentium Pro with a 512 KB L2 cache PGA package. 200 MHz Pentium Pro with a 1 MB L2 cache in PPGA package. Uncapped Pentium Pro 256 KB summary. The Pentium Pro incorporated a new microarchitecture different from the Pentium's 5P microarchitecture. It has a decoupled, 14-stage superpipe-aligned architecture which used an instruction pool. The Pentium Pro 6P implemented many radical architectural differences mirroring other contemporary x86 designs such as the next-gen NX586 and Cyrix 6x86. The Pentium Pro pipeline had extra decode stages to dynamically translate IA32 instructions into buffered micro-operation sequences which could then be analyzed, reordered, and renamed in order to detect parallelizable operations that may be issued to more than one execution unit at once. The Pentium Pro thus featured out-of-order execution, including speculative execution via register renaming. It also had a wider 36-bit address bus, usable by physical address extension, PAE, allowing it to access up to 64 GB of memory. The Pentium Pro has an 8 KB instruction cache, from which up to 16 bytes are fetched on each cycle and sent to the instruction decoders. There are 3 instruction decoders. The decoders are unequal in ability. Only one can decode any x86 instruction, while the other 2 can only decode simple x86 instructions. This restricts the Pentium Pro's ability to decode multiple instructions simultaneously, limiting superscalar execution. x86 instructions are decoded into 118-bit micro-operations, micro-ops. The micro-ops are reduced instruction set computer, RISC, like. That is, they encode an operation, 2 sources, and a destination. The general decoder can generate up to 4 micro-ops per cycle, whereas the simple decoders can generate 1 micro-op each per cycle. Thus, x86 instructions that operate on the memory, for example, add this register to this location in the memory, can only be processed by the general decoder, as this operation requires a minimum of 3 micro-ops. Likewise, the simple decoders are limited to instructions that can be translated into 1 micro-op. Instructions that require more micro-ops than 4 are translated with the assistance of a sequencer, which generates the required micro-ops over multiple clock cycles. The Pentium Pro was first processor in the x86 family to support upgradable microcode under BIOS and /or operating system, OS, control. 5. Micro-ops exit the reorder buffer, ROB, and enter a reserve station, RS, where they await dispatch to the execution units. In each clock cycle, up to 5 micro-ops can be dispatched to 5 execution units. The Pentium Pro has a total of 6 execution units, 2 integer units, 1 floating point unit, FPU, a load unit, story address unit, and a store data unit. 6. One of the integer units shares the same ports as the FPU, and therefore the Pentium Pro can only dispatch one integer micro-op and one floating point micro-op, or two integer micro-ops per cycle, in addition to micro-ops for the other three execution units. Of the two integer units, only thing that shares the path with the FPU on port 0 has the full complement of functions such as a barrel shifter, multiplier, divider, and support for LEA instructions. The second integer unit, which is connected to port 1, does not have ethers facilities and is limited to simple operations such as add, subtract, and the calculation of branch target addresses. 6. The FPU executes floating point operations. Addition and multiplication are pipelined and have a latency of 3 and 5 cycles, respectively. Division and square root are not pipelined and are executed in separate units that share the FPU's ports. Division and square root have a latency of 18 to 36 and 29 to 69 cycles, respectively. The smallest number is for single precision, 32-bit, floating point numbers, and the largest for extended precision, 80-bit, numbers. Division and square root can operate simultaneously with adds and multiplies, preventing them from executing only when the result has to be stored in the ROB. After the microprocessor was released, a bug was discovered in the floating point unit, commonly called the Pentium Pro and Pentium 2 FPU bug, and by Intel as the flag erratum. The bug occurs under some circumstances during floating point to integer conversion when the floating point number will not fit into decimal integer format, causing the FPU to deviate from its documented behavior. The bug is considered to be minor and occurs under such special circumstances that very few, if any, software programs are affected. The Pentium Pro 6P microarchitecture was used in one form or another by Intel for more than a decade. The pipeline would scale from its initial 150 MHz start, all the way up to 1.4 GHz with the dualate in Pentium 3. The design's various trays would continue after that in the derivative core called banias in Pentium M and Intel Core, Yona, which itself would evolve into the Core microarchitecture, Core 2 processor, in 2006 and Downward. 7. Instruction set. The Pentium Pro 6P introduced new instructions into the Intel range. The CMOVXX, conditional move, instructions can move a value that is either the contents of a register or memory location into another register or not, according to some predicate logical condition XX on the flag's register, XX being a flag's predicate code as given in the condition for conditional jump instructions. So for example, CMOV moves a specified value into a register or not depending on whether the NE, not equal, condition is true in the flag's register, i.e. Z flag equals 0. This allows the evaluation of if-then-else operations, and for example the operation in CTC instructions give a performance boost by allowing the avoidance of costly jump and branch instructions. In ECMOVX distreg 1. Source underscore operand 2. The first operand is the destination register, the second the source register or memory location. The second operand unfortunately cannot be an immediate, inline constant value, and such a constant would have to be placed in a register first. The predicate code XX can take the full range of values as allowed in conditional branches. A second development was the documentation of the U2 illegal instruction. This opcode is reserved and guaranteed to cause an illegal instruction exception on the 6P and all later processors. This allows developers to easily crash the current program in a future-proof fashion when a bug is detected by software. Performance. Despite being advanced for the time, the Pentium Pro's out-of-order register renaming architecture had trouble running 16-bit code and mixed code, 8-bit with 16-bit, 8/16, or 16-bit with 32-bit, 16/32, as using partial registers cause frequent pipeline flushing. 8. Specific use of partial registers was then a common performance optimization, as it incurred no performance penalty on pre-P6 Intel processors. Also, the dominant operating systems at the time of the Pentium Pro's release were 16-bit DOS and mixed 16/32-bit Windows 3.1x and Windows 95. Although the latter requires a 32-bit 80386 CPU, much of its code is still 16-bit for performance reasons, such as user.exe. This, with the high cost of Pentium Pro systems, led to tepid sales among peak buyers at the time. To fully use the Pentium Pro 6P microarchitecture, a fully 32-bit operating system is needed, such as Windows NT, Linux, Unix, or OS/2. The performance issues on legacy code were later partly mitigated by Intel with the Pentium 2. Compared to RISC microprocessors, the Pentium Pro, when introduced, slightly outperformed the fastest RISC microprocessors on integer performance when running the SPECint 95 benchmark, 9. But floating point performance was significantly lower, half that of some RISC microprocessors. 9. The Pentium Pro's integer performance lead disappeared rapidly, first overtaken by the MIPS Technologies R10000 in January 1996, and then by Digital Equipment Corporation's EV56 variant of the Alpha 21164.10. Reviewers quickly noted the very slow writes to video memory as the weak spot of the 6P platform, with performance here being as low as 10% of an identically clocked Pentium system in benchmarks such as VID-SPED. Methods to circumvent this included setting VESA drawing to system memory instead of video memory in games such as Quake 11, and later on utilities such as FastVid emerged, which could double performance in certain games by enabling the right combining features of the CPU. 12, 13. Memory type range registers, MTRs, are set automatically by Windows video drivers starting from 1997, and their improved cache/memory subsystem and FPU performance caused it to outclass the Pentium Clock 4 clock. In the emerging 3D games of the mid to late 1990s, particularly when using NT4. However, its lack of MM's implementation reduces performance in multimedia applications that made use of those instructions. Caching. Likely Pentium Pro's most noticeable addition was its on-package L2 cache, which ranged from 256 kilobytes at introduction to 1 megabyte in 1997. At the time, manufacturing technology did not feasibly allow a large L2 cache to be integrated into the processor core. Intel instead placed the L2 die-S separately in the package, which still allowed it to run at the same clock speed as the CPU core. Additionally, unlike most motherboard-based caches CHEMs that shared the main system bus with the CPU, the Pentium Pro's cache had its own backside bus, called Dual Independent Bus by Intel. Because of this, the CPU could read main memory and cache concurrently, greatly reducing a traditional bottleneck. 14. The cache was also non-blocking, meaning that the processor could issue more than one cache request at a time, up to 4, reducing cache miss penalties. This is an example of MLP, memory level parallelism. These properties combined to produce an L2 cache that was immensely faster than the motherboard-based caches of older processors. This cache alone gave the CPU an advantage in input forward/output performance over older x86 CPUs. In multiprocessor configurations, Pentium Pro's integrated cache skyrocketed performance in comparison to architectures which had each CPU sharing a central cache. However, this far faster L2 cache did come with some complications. The Pentium Pro's on-package cache arrangement was unique. The processor and the cache were on separate dies in the same package and connected closely by a full-speed bus. The 2 or 3 dies had to be bonded together early in the production process, before testing was possible. This meant that a single, tiny flaw in either die made it necessary